And that is what the inventors community is all about. I mean, we are not planning to touch everything for you. I mean, it's definitely impossible, right? But we want to just do it in such a way that you can stand on your own. When you get to the point where you can now learn and build on it on your own, that's the point we want to get to. And at any point during this conversation or during this lecture, you can stop me to ask your questions, because I mean, we don't want to, maybe at the beginning of the session something is not clear to you, and we've built a lot of things on that, and at the end of the class you're not trying to ask a question that's something we've talked about at the beginning. You end up being getting confused throughout the class. And I mean, a lot of people know me. I've missed this, to be honest. I mean, it has been a while that I've been in this session where I get to lecture the inventors again. So it's really been a while. So I must say, hope I still have my juice, basically. So I have a slide prepared, and yeah, it's just going to serve as a guide. Definitely, I'm going to be switching between the slide and my IDA, where we're going to be writing some codes and we're going to be demonstrating some things. So let me quickly share my screen and get started. Okay, for some reason. Okay, so basically I've already introduced us to the class, and I've introduced myself. And I mean, this is the first class of the data structure and algorithm series we'll be having for the next 4 weeks. And for this class, these are the things we are going to be basically talking about some history of some little things we need to know about the history of data structure and algorithm. We're going to talk about introduction to how the computer store and processes data. Just going to talk about a little bit more about that for, maybe beginners that are in here among us. Then we're going to talk about big O notation in general. I'm going to give some insight about it. Then we are going to talk a little bit about time and space complexity, and we are going to be talking about the array data structure. So those are the things that we intend talking about today. And yeah, so in next class we definitely have some extra data structures we'll be talking about, and some other algorithms like search and sorting algorithms, etc. But this is the scope. This is the scope of today's class, and yeah, this is everything we intend to touch on today. So yeah, so without further ado, I think I have about 45 minutes, so I'm just going to try as much as possible to deliver as much as I can within that time. So we'll start with the issue of data structure and algorithm. But I figure out that nobody cares about this, so it really doesn't matter about what the history is. We just want to know what it is, right? So we're going to jump to the next. So basically, we're going to be giving a little insight on how your data is represented in the memory. So before I continue about that, I'm going to really sort of explain what kind of memories we're talking about. Now, for the beginners here or for really experts here, we have two types of memory. We have the volatile and the non-volatile ones. So we have, the memory, and we have the storage, basically. So your storage is basically your hard disk, anywhere. I mean, your solid state drives, your drives, basically. And the memory revolves around your computer memory. That's the read and random access memory, mostly the RAM, right? And most of the things we are going to be talking about, when I mean once you turn off your laptop, everything on your RAM wipes off. And once you turn it back on, some things are being written back onto your RAM. So that's volatile memory. So I give an instance here, and I'm just going to try as much as possible to explain it as much as I can. Like I said, if you have a question, you can as well just turn on your mic and speak. So I'm just going to keep quiet immediately and let you basically see what you have to say. Now, take for instance, I don't know which languages we write. But the scope of this class is going to be based on Java. So I'm going to be doing more explanations on Java, but nothing about the semantics of the language itself. It's just going to be around, the building blocks of programming in general. So it's something that you can all relate to here. So first of all, if you're declaring the variable while writing your code, for instance, and you're declaring a variable and you say a equals to 5, for instance. Now, how does the computer understand this? How does the computer represent this? Now, in school, we need to know that 8 bits makes 1 byte, right? So let's say, for instance, this is your memory. And these are memory locations basically. And I label them awkwardly because this is not how the computer labels your memory. Basically, is always going to be some characters, 0x, I mean, it's written in some sort of weird way. But just so that I can explain today, and it's going to be easy to visualize, I have numbered it like this, like 1 to 20, right? So these are memory spaces. I mean, this is, for instance, this is 1 byte, this is another byte, this is 1 byte, another byte. And I mean, let's say, for instance, you have about a 4 gig RAM or a 16 gig RAM, you know how many bytes you have to store information. Now, each of these is 1 byte, and 1 byte consists of 8 bits, right? 8 bits. Sorry, I didn't represent that here, but yeah, 1 byte equals to 8 bits. Now, if you want to represent these, integers generally have been they are given mostly 4 bytes of memory space. So, if you find an integer, the memory space allocated by your computer is mostly 4 bytes. 4 bytes for any integer you are declaring. So if I'm declaring a equals to 5, the computer has set up 4 bytes in the memory for you. So just to explain, I think I'll just make this easy and sort of add some little bit of text here. So just to make it more explanatory. So I'm going to say, 1 second. Okay. So like I said, 8 bits. So 8 bits equals to 1 byte. And for integers, it gets awarded by integer, you get 4 bytes generally. So this is what it is. Now, if you are going to represent this in binary form, I'm very sure we sort of know how to convert decimal numbers to binary numbers. We divide by 2, you traverse it downward, then so for to convert 5 to binary, it is 1 in base 2, 101 in base 2. But how does your computer store this 101 in the memory, right? Now, since you have about 32 bits, I mean 4 bytes for this, that means you have about 32. So for this, if you have 4 bytes, 4 bytes equals to 32 bits, right? So let me just put it in front here. Let me just separate it and say 4 bytes. As represented in 32 bits integer, it's going to add 29 zeros, 30, 31, 32. This is 5 on your memory. So this is how the computer represents this value in memory. If it is 6, it converts. If it is 6.5, definitely is to convert it down to binary. Now, how do we save this binary on your memory location? Now, this is 1 byte, this is 2 bytes, this is 3 bytes, this is 4 bytes. Now it's going to store this value, this 32 bits, in 4 contiguous locations, right? The first 8 zeros here, the second 8 zeros here, the third 8 zeros here, and it starts from this memory location. That's number 5, and 4. If it's an integer, it allocates 4. If it's maybe a string that needs about 10 bytes, then allocate 10 bytes for that value, depending on the character encoding for that string. Now, I'm not going to dwell too much on this because, like I said, we do not have too much time. So I'm just going to talk about algorithm big O notation in general. Like rightly said, we are basically using this to guide me through the class, right? I mean, this does not do justice to what I really have to say. Like I said, you have to pay attention and put things down. Now, let's take for instance, let me play an hypothetical situation. Now we have about let's not represent this as memory again. Let's take for instance that these are cities. This is city 1, city 2, city 3, city 4, city 5, city 6. Now each of them has what they are good for. Let's say this city, they have let's say natural resources, they have gold, for instance. Forgive me, this one has silver, this one has bronze, and etc like that. And let's say here this one has, let's say, ceramic, right? Sorry, it's a bit messed up now, but yeah, let's say these are cities, right? And you have a bird here, or let's say a plane here, right? And now we need to find which city has ceramic, right? Now, what does the plane has to do? It has to fly across each city, right? Till it gets to 11, where it finds ceramic. Now, this is basically what how your computer mostly traverse through your data structures like arrays. And I'm going to get into arrays very soon. But this is just the idea of how algorithm complexity works, basically. The amount of work that your CPU has to do, or the amount of time that your CPU has to spend before getting the right information or before processing your information, before completing processing. That is what algorithm complexity is about. Now, big O notation. Big O notation is just forgive this. This is big English, but basically it's just a way to represent how complex an algorithm is, right? And as I mentioned here, it's a way to measure an algorithm's efficiency. And first of all, if I did not define what an algorithm is in the first place, I would like to do. Algorithm is just like a step-by-step procedure that enables you to perform a specific action in your code. So let's take, for instance, your code is supposed to you're supposed to write a code that calculates the area of a triangle. And on your code, you write your function, you write your step-by-step process in solving that particular problem. Now, that small function you wrote is an algorithm. Now, how do we calculate the efficiency of the algorithm? That's okay, we're able to solve that particular problem, but were you able to solve it efficiently? And those are the things we're going to be touching on in today's class, right? It measures the times it takes to run your function as the input grows. It describes an algorithm's runtime when the input tends towards the specific or limiting value. It helps to analyze the algorithm performance change in the order of input size. We use this to analyze both the worst case time and space complexity of an algorithm. Now, before we do this, I would like to just give us an insight of what the array algorithm, the array data structure is about. And I think by then to give us more insight of what big O notation is, so I think it just makes sense to swap this. Now, what is the array data structure? Simple, and I'm just going to explain how it is represented in your memory again, and maybe that's then we'll be able to take us to how we analyze it in codes, and I'm going to be showing us some code examples, right? Now, an array is a linear data structure that collects elements of the same data type. Now, this statement is not always true for all languages, right? For the same data type, but ideally, this is what an array should be. Now you see some languages like PHP, where you declare many arrays and you can put in any data structures you like in there, or I think JavaScript in some cases. Now, an array generally should take elements of the same data types and store them in contiguous and adjacent memory locations. Now, I already explained how, for instance, I will save integers, a single integer in the memory, for instance. Like I said, please, if you have any question, you can always just turn on your mic and say something, and I may be able to answer it. Now, you have the array data structure, for instance, and I declare an array and I named it A, and this array contains five values, five integers, and these are the integers 3, 14, 8, 9, and 43. Now, we already know how this represents 4 bytes, right? So this takes 4 bytes. Sorry, I do not have the time to start calculating this in binary, but it doesn't matter because I just want us to be able to visualize this, right? So it stores this in the first 4 bytes. Now for arrays, right, it has to look for and for arrays in general, you have to declare the size of the array, right? You have to declare the size first. So you are telling the computer that you need about 5 memory spaces. Basically, for integers is 4 bytes each, and for this you are going to take about 20 bytes of your memory, right? That's going to save 5 integers, for instance, and this one takes the first 4. This one takes of like I said, it's going to be represented in the binary format, but who cares, right? So 3, 4, 8, 19, and 43. Now each of these have a way to retrieve them. For instance, we have something we call array indexes, right? If I want to access this value, there's a way I access them. And for this, I'm basically just going to stroll to my IDE here. And if you can see my screen, my IDE, please let me know. If I need to zoom in, please let me know. If it's okay this way, please let me know. Okay, so I'll take that as a go ahead. So let's take, for instance, I'm declaring this data structure, this integer data structure, an array of 5 elements here, right? So now, How do we access the first value here, for instance, if I'm trying to retrieve this? I'm going to just simply be printing on my console. So system.out.print line, and I'm going to print in, sorry, at 0, for instance. If I run this code, I'm going to get 3. So basically for arrays, it starts from 0. This is 1, this is 2, this is 3, and this is 4 in general. So now if I run this code, for instance, I don't think I have to save. Good. You get this, ignore this. I mean, this is just me editing my group space. But yeah, you get 3, right? And if I want to get 8, I just access it by using 2, right? And when I run this, I'm going to be getting my 8. So this is basically an array data structure, right? And you have 5 elements in it. Of course, you can declare more elements in there, and I mean you call them out by using this value. Now, what does this value represent on your memory, right? This array contains a pointer. So there's going to call pointers to the base location. So for 3, for instance, 1 will be the location. Like I said, this is not how it is represented. Basically, this is not the numbers you get to see when it comes to memory, but then there's a very funny way, exactly my format. I don't know this is being represented. Now, if for instance, like I said, like I was making an instance about you're trying to fly a plane, right? And I'm looking for a city that has this value 19. That means I need to go through this one, this one, this one, and this one to get this value 19, right? And that's it about arrays. I mean, to access it, you either have the index or you have to search through the array to be able to get the value. That's if you are looking for a value in an array, for instance. Now, what does time complexity mean? Type complexity means when you write your code, how many times does your processor have to go through things like this, like search through your algorithms or search through your data to be able to get what you want? And there's time complexity, of course, and there's space complexity. How many memory locations, like what's the space that this data is taking in your code, I mean, your memory, basically. Now, which one is more important, the time or the space complexity? Most times, because I mean, technology has advanced. Space to buy more memory is now more cheap. Like it's just cheap to get memory, right? But you can't buy time basically. So most of the time, people pay more attention to the time complexity of an algorithm as opposed to the space. The time is more important, right? For all of us, we want something that we'll be able to do and it gets processed fast. Now, if you are consuming too much memory, nobody cares, right? Because you can easily buy memory space as much as you want, right? So that is why time complexity is mostly paid more attention to. But of course, in interviews, you get to be asked what space complexity of an algorithm, etc. Right? So it's important that we know that as well. But just know that when you're writing your code, right, pay more attention to which one consumes less or which one consumes more. That's more important. I mean, in terms of time, basically. So yeah, interestingly, I would now talk about, or basically let's basically write a code to search for an integer within this array, for instance, right? So let's say for instance in this array, right, I'm looking for a value, let's say 19, and I do not know the index. Now, this is very easy to visualize because we just have 5 elements in this array. But you can be solving a problem where, for instance, you have a million of this kind of data or a billion, for instance, right? And you're supposed to search through it. Now, of course, there are different type of arrays. We have the sorted and unsorted ones, but I'll be paying more attention to arrays that are not sorted because next class we're going to be talking more about sorting algorithms, binary search, etc. So those are search algorithms really. Now, how do I write the code to do that? I mean, it's simple, right? You just maybe write a simple for loop or for each loop, depending on how you prefer it. So let me do the for loop here. I think that's easy for everyone to visualize. So for entire equals to 0, we're going to start traversing from 0. So that's I less than or equals to a dot less than a dot length, then I dot, right. So now we are trying to traverse through this array. And how do we find if this is 19? We just say if a at I, sorry, a at I. We're just trying to search if an element is present in this array. Let's try to search if 19 is present in this array, for instance. And if it is present, let's just display true. If it is not, we display false, right? So if a does get equals to 19, because we're trying to look for 19, we can say it should display true, right? And if it is not, I mean, if at the end of the day it doesn't display true, I'll just try to put this in a function anyway. So let me just say static sorry, static search. It's a boolean or a string. It's a string. Search array and say integer value that you're searching. I'll do the same here. Good. So that's in the array as well. Value. Yeah, cool. So if after this return true, and here is return false. Okay, cool. So here we say search array and we're passing a and passing 19. And for instance, we're searching through this array for this value 19, right? And here basically is just going to look through every element in this array, right? And it's going to check if this value exists. If it exists, right? It returns this. If it doesn't exist, it returns this. So let me just print it out here. System print line. If I run this, I mean, it gets true because, of course, 19 is present. But what happened here? This for loop has to check this and check this and check this. And when it goes to 19, it stops checking, right? That is what this basic algorithm did. Now, if you have data as long as maybe 12 billion data, for instance, that means your processor has to go through about 12 billion data depending on where the value you're searching for is. And that brings us to what big O notation is basically. Big O notation is just a way for you to generally present or denote how fast your algorithm is. I mean, what is the best case, the worst case, or the average case scenario of your algorithm. But as, of course, we are scientists, right? We are pessimistic set of people, right? So we generally take a look at the worst case scenario, and that is what big O generally is. So
Yeah, sorry to
coming back
break
to
you, John.
Sorry
this,
to break you, John.
Someone is raising their
all
hand.
right.
Someone is raising their hand.
Okay, sorry. I mean, like I said, please turn off your mic immediately and ask, right? Turn on your mic immediately and ask because I was not looking at the chat. So go ahead and ask, please.
Yeah, I'm no, I just want the code. I want to ask if you can paste the code on the chat. This the code I just wrote down, please.
Okay, so cool.
Yeah, thanks.
No worries. Okay, I don't need to copy. I just copy the main method and paste for you. It's going to look ugly, you know. Let's just manage it. All right, cool. So now, just imagine, like I said, you have about 3 billion data traversing through. It's going to be difficult, right? I mean, of course, your CPU is fast, right? And it's going to try as much as possible to go through each and every one of the values here before it gets to that particular value you're looking for, right? So now, imagine a case, like I said, where you are trying to search a trillion variables and you're searching like this. how efficient would it be for you to now take a look at every element in this array before you get to that particular one you are finding? Now, let's take for instance, what is the complex algorithm complexity of an array when you're trying to search through an array? And that is what I'm going to explain in this next part, talking about big O notation. So now there's something we call time complexity. I already explained space complexity, and I will use this example, right, to explain what both of them means. Now we have worst case time complexity. Did I just edit? Okay. And it just basically explains the maximum amount of time an algorithm requires to consider all input values represented by big O. And like I said, this is what is most important. Nobody will ask you for, I mean, some cases you get in an interview where you ask for the best case time complexity. But if you're solving a question in an interview, for instance, it is just expected for you of you to, after writing your algorithm, you sort of explain that this algorithm runs in O of something, O of something. I mean, you just calculate the worst case time complexity in that case because, well, we want to know if at worst, what are we going to get from this algorithm? Now, for worst case scenario for this particular algorithm, for this particular case that I wrote for this particular code, is the worst case scenario here will be if you're looking for 43, right? If you're looking for 43, that means you have to go through 1, 2, 3, 4, 5. So worst case scenario will be if you're looking for the last value here. And how do we represent this in big O notation? We represent this as big O, that's O of what's n. And what is n? Sorry, this is not code, right? That's why you're going to be saying it this way. So let me just put that as a comment. And what is n? N here simply means the number of elements in this array. Because if you have more here, 19, let's say 900, I can put too much 19 there, let's say 600 for instance. The worst case time complexity of this algorithm will be when you are looking for 600. And 600 simply represents 1, 2, 3, 4, 5, 6, 7, 8, which is basically the length of this array, right? So the worst case scenario of looking for an element in an array would be when the element is the last element. If you get me. So what would be so for searching an element in an array, the worst case scenario would be when you are picking the element that is last, right? That's the worst case scenario. And we come back here, the best case scenario. The best case time complexity requires the minimum amount of time requires to consider the minimum amount of time. Now, the best case scenario to search through all the elements in this, to search through an element in this array is if the element is the first. That is, it doesn't need to search everything. No need to search through the first, which is big O of 1. Because it's only searching once. Now, n here could mean anything. But here, n being the number of elements in this array, right? Because you don't know the number of elements. So if you are asked in general that what is the time complexity to search through an element for an element in an array, the worst case scenario is if the element is the last, and that is dependent on the amount of elements here. Now, if you're saying you're looking for 14, you can see it's O of 2, right? O of 3 if you're looking for 8, but then you're looking for an array in general. An array can contain 5 billion, 6 billion. The worst case is if it's the 6 billionth value, and that is n. So we see O of n, where n equals to number of elements in the array. Forgive me, I typed fast, but yeah, that's what it is. So this is a worst case scenario. Now, for the best cases, if the element is the first here, and it's just simply O of 1. If I'm looking for 3 in this algorithm, for instance, I mean this array, for instance, I don't need to search through everything. It just goes through picks the first one for me and returns it, right? According to this code, it doesn't have to search through each and every one of these to be able to give me this value. And what's the average case scenario? It's probably average case scenario are the scenarios between the worst case and the best case. So if you're looking for 43, for instance, consider the average case scenario.
Yeah, sorry, John.
But
Sorry
like I
to
said,
break you.
the units are used. All right,
Someone is
all
raising their
right.
hand. Yeah.
Go ahead. Please go ahead. I mean, just open your mic and ask your question. I will just stop immediately.
Oh,
Go
okay,
ahead.
sorry. Good evening.
Good evening.
I just want to clarify what you said. Does it mean
Okay.
worst case scenario? Does it mean that it's considered when, like, for instance, the larger the number of inputs, right?
Yes.
So for
Yes.
best case, if
So
there's a smaller number of input, then you're looking at the best case, right?
no, No, okay, so I'm going to try to break it down. Now, like I said, this array could be as large as 50 billion records. I mean, nobody's going to start typing 50 billion records here, but I mean, you can have scenarios where you need to read from a file and you have a lot of records in there, right? Now, let's just take this array for an instance. We have about how many elements here? 1, 2, 3, 4, 5, 6, 7, 8. Now, to search for an element inside this array, what is no? Let's take for instance, you do not even know the element you're looking for, right? To search for elements in this array, the worst case scenario would be if the element is the last. That is, your computer will need to take a look at every location in the memory, looking for that element until it gets to the last. So it's just a case of asking, if I'm looking for an element in an array, what is the worst that can happen? The worst that can happen is if you are trying to look for 600 in this array, for instance. Now, 600 in this array is the last number. I mean, it's just dependent. So what if I have other values in between here? And let me say I have 1000 values here, and 600 is not among them. The worst case scenario is to be if you are looking for an element in the array, and the value you are looking for it is the last element in that array. The last element in this array is at index 7, and that's the 8th element. And another value was here, let's say 50. The worst case scenario will be you're looking for 50, which is the last element. And the last element here is what? It's still the 9th element, which is the length of this array. So what we are trying to say here is that the worst case scenario of looking for an element in an array is when you are looking for the last value. And if you're looking for the last value, that means you have basically gone through the entire element in the array, right? So that means to get the worst case scenario of searching for an element in an array is O of n, and n being the number of elements in the array. For this particular array, for instance, this 8, right? The worst case scenario of searching here is O of 8, but I mean, we don't represent it that way because you are dealing with a case where sometimes you are given an array where you do not even know the length, right? So the worst case scenario of looking for an element in an array is when the value is the last element in the array. I don't know if I explained correctly. And if you, is that clear? Faiza, I mean, is that, if I got your name correctly?
Yeah, it's clear. Thank you.
You sure? Okay, cool. So yeah, so I mean the best case scenario. So let me just make this an instance, right? Like you are trying to, I was trying to use cities as an instance the other time, right? You have a bird or a plane that can fly through cities, right? This is the first city, this is the second, this is the third, this is the fourth, etc. Let's say this ones represent different things: gold, ceramic, bronze, and let's say silver happens to be at the last city. For your plane to be able to look for the city that has silver, it has to fly through all the cities, right? To get to the last one, to get the value. So let's take, for instance, you now have 1 billion city. Your plane has to definitely fly over 1 billion cities to be able to get to that city that finally has silver in it, right? So the worst case scenario, your plane is going to fly as much as the number of cities generally. So that's the worst case scenario. The worst case is when your plane has to fly over all the cities. So and all the number of cities is unknown. For instance, here is n, and like I said, it could increase in number. You can have billion values here. But the best case scenario is if you are lucky enough. The best case scenario is if what you're looking for is the first element. So the best case scenario would be 3. I mean, if you're looking for 3 in this array, for instance. So yeah, that's how I explained it. So yeah, basically that is for searching through an array. Now to add an element in an array, for instance, I'm going to add something else in this array, for instance, and I want to add something to another index. Now let me just basically complete conversations about how array works in terms of data memory. Now, like I said, your memory is going to look for contiguous space, right? I mean bits in your memory locations and represent your array there. So for instance, I have 5 here. Let's take for instance something was already here before, right? This is going to start counting from here to here just to look for enough space because you're already going to declare the number of elements in the array to represent this, right? Now, Now let's take for instance, I am trying to increase the size of this array. To increase the size of an array, the computer basically look for another space, right, in your data. For instance, here, for instance, I'm trying to say a at 9 equals to, let's see, 200. We have it already. I'm trying to add another element here. Okay, let me just remove this. Now let's, for instance, at space 21 here, something already exists in that memory space, right? Now, if your computer needs to add another element in an array, it has to look for another contiguous space that can take this number of elements. That means 6 in this case. This one is 5. That's why you can see 5 spaces here. Let's say, for instance, we have more byte spaces here, right? Look for another memory space on your random access memory, basically, to that can contain 6 elements and copy all these values over here. So basically increasing the number of elements in your array, I mean, after you declared it directly here, takes more time. Because
Heads up.
after the computer looks for another space, it has to copy each and every one of these to that new memory space. Like, I think that is not super. So yeah, basically in general, operations on an array. When you're searching through an array, which is what I just explained. Like I said, we're going to be talking mostly on the worst case time complexity because that is the most important. As scientists, you're supposed to be as pessimistic as possible. Well, so you're going to be using this big O notation. So in general, if you are going to be asked what is the time complexity of an algorithm, the first thing that comes to your mind is to look for the worst case time complexity of that particular algorithm. Now, to search through an array, it's O of n because you're going to be needing to go through each and every element. And the worst case is when the element is the last, right? The best case is O of 1. Average is when it's in the middle, which could be O of 2 or whatever. Then insertion, when you're inserting a new element in an array, is O of 1. I mean, to you, because you're just adding another value to it. The best case of also is O of 1. And to delete an element is O of n, because in most cases, when you delete an element on an array, for instance, you delete something from this memory location, for instance, this 14. In most cases, you need to copy these values back. It's different from when you're setting this value to null. Null is also a value. It just simply means this value contains null. When you are deleting something from an array and you are shifting each of these values backwards, then the time complexity is O of n, O of n minus 1 was, but you can eliminate constants in most cases. So that is when you're trying to delete an element. So the worst case here is when you're trying to delete this element here. Sorry, when you're trying to delete 3, I mean, it has to copy 1, 2, 3, 4 back to this location, basically. So it has to copy like about 4 values, really. So that's for deleting elements in an array. Now let's talk about let's write some algorithms, some codes, and how you can best describe the algorithm complexity. Because I mean, we just use this to explain the basics, right? To search for elements in an array, this is it, best case, etc. But of course, like I said, we're always going to pay attention on the worst case time complexity. Now, if I'm writing an array, for instance, I mean an algorithm, for instance, like a function, and this function is supposed to let me know, trying to look for a random question here. Okay, so let's declare another integer array here. And because I'm lazy, I'm just going to copy and paste. And I'm just going to just change some things here. Let's say 114, let's say 80, let's say 190, etc. And let's just delete the rest. Now, you're asked to search through these two arrays, for instance, and tell us if the value 190 exists or the value 80 exists. It simply means that you're going to search through A first, right? And you're going to search through B. And if you're writing that such an algorithm in this function, how are you going to represent the complexity? Because you have two different arrays here, right? Of sizes that you do not know. Like I said, sometimes you're given questions where you have a billion values here, and all you need to know is, okay, an array is going to be passed, an array B is going to be passed to your function. Now let us know the complexity of searching for an element between these two arrays. Now, how will you write the code? You basically search through A like you just did here, and you do the same thing for B here, right? And you search through B as well. So B dot length, and this is going to be B. Okay, I'm going to need to pass B into this function. So B is going to be here. Search through A, search B, and if you can find the value, return true. If you can't find the value, return false. Now, what is the algorithm complexity of this? Because you don't get to say O of n. N means the number of elements in the array, right? But there are two different arrays here, right? How do you represent this? Now you can see the algorithm complexity of this particular algorithm. Okay, let's pass in B here now. This works. Okay. Now, what is the complexity of searching through these two algorithms? We wrote a code like this, for instance. You ask, what is the complexity of this algorithm? Remember, you've searched through the first array and you're searching through the second array as well. Now, the algorithm complexity of this, you can say it is O. Sorry, I'm going to O of can be an arbitrary value. You can say n plus p. And you can see where n equals to number of elements in array A. Like I said, I'm lazy, so I'm not going to be correcting the typos here. And P equals to number of elements in array B. Array B. Now, why is the complexity n plus P? Because two guys have different lengths, which you do not know. Now, like I said, the worst case scenario of searching through this algorithm is if we are looking for 190. Or let's take, for instance, you're even looking for a value that is not present in this area at all. Right? That means it has to go through all of this and go through all of this as well. Now, we represent n as the number of elements in array A and P as the number of elements in array B. That is how to calculate in this case, right? Now, let's take, for instance, you now have an hypothetical situation where you need to search for elements in array A twice. So first of all, let me just state the rules here. So if you are searching through arrays, searching, so I'm going to like try to share this. So sorry if you can not hear me. I mean, if you can hear me, just say hi.
Hi.
Hi. Hi.
If you can hear me,
Hi, I
you
can
can
hear
hear
you.
me. Okay. Okay. So I just okay. Sorry about that. So my network, someone was trying to call in, and it was disrupting my network. All right. Cool. So yeah. So basically, sorry. Give me a second. Just to unrecord this. Oh, okay. Someone is trying to say I've exhausted my time, which is crazy, right? But yeah, I'm going to be sharing some resources, right? Because, like I said, basically we just need to get the ideas, right, on how you calculate algorithm complexity. So if you're writing codes, for instance, where you need to process a lot of things, right? I mean, this is just the first class, and we still have 3 more classes to go. And I think the last class is going to be free, a bit of solving real life questions, right? We're just going to pick some real life problems like in Akarank and try to solve them in maybe worst time complexity and best time complexity as well, right? And I'm going to be seeing it. But basically, like I said, I'm going to be sharing some resources on algorithm complexity, time and space complexity, and definitely, like I said, it's going to be explaining it better because like I tried to squeeze this into 1 hour, and which is not enough time. We do not know if there will be a campaign to stretch this class more than 4 classes, but for now, we have 4 classes, and I'm just going to stop here today. So I'm going to share some resources with the leads after this class. And if you need those resources personally, you can get to me through. If you have my number, you can message me. Anybody, if you need to get to me, you can get to me through whoever, whichever platform like you got these links from. So if you got it through Twitter, you can go through Twitter to ask for those resources. If you saw it through LinkedIn, you can go to LinkedIn and message Inventors page personally to get those. If you got this link through a friend, you can message that friend to get this link from me. So it's going to basically be explaining arrays in general, complexity, and how you calculate time and space complexity for arrays. I think I've done justice on how you search through two different types of array, one, and the other ways in which you calculate, like eliminating constants, for instance. For instance, this algorithm A twice, the algorithm complexity is not O of 2n, it's still O of n at the end of the day. But yeah, there are some rules to it that we're going to pass across in the resource we're going to be sending. So thank you so much. If you have any question at this point, because we try as much as possible not to waste time in our classes, and that's just what Inventors is, right? So it's best you try to join early so that we don't end up finishing late. So 3 minutes late. So if you have any questions, please let me know.
Hello, sir.
Yeah, go ahead.
Yes, sir. The question is, in searching an array, like, what do we do when we have repeated values, like having 299?
You can have repeated values in an array. It's allowed. It doesn't. It takes duplicates. You can have an array containing only 99s.
Okay, sir.
Yeah. Any other question? So thank you so much,
Sorry,
since
boss. I have a
everyone.
question.
Okay, go ahead, sir. Okay, okay,
So,
go ahead.
so basically, based
Yeah.
on the feedback, um, one of us dropped on the chat platform now, chats
Okay, good.
page.
I'm trying to
So
check.
the goal of every algo then is to try to minimize um, the worst case scenario, the worst case time complexity then.
Yeah.
So as much as possible, try to
Yeah,
eliminate,
to cut it down.
try to
Yeah.
cut it down. Sure.
Yeah, that's the goal. Like I said, space complexity is important, but right now, people, I mean, you can buy space, right? Everybody does, right? If you're building systems that are worth, processing billions of data, you can buy space. But I mean, people want to be able to process, I mean, send information to the computer and get it processed quickly. And that is why it is very important for you to minimize the time complexity as much as possible.
Thank
So,
you. Thank
so
you.
okay. So by the way, Emmanuel that just asked the question was my colleague at Paga, and I will say thank you for joining us today. Who else has a question to ask? I mean, you can drop it on the chat. Can you drop my number? Yes, I mean, I think almost you can get it from Elijah. I don't know if it's safe to. Yeah, I can drop it. And you can message me on WhatsApp. I'm on all the Inventors social media platform. So yeah, I just type it too. Yeah, so this is my number. Any other question? Like I said, we're trying not to waste our time. So yeah, join us. I mean, same time next week, 8 p.m. And please try as much as possible to join earlier so that the moderator for next week will be able to. Okay, Elijah, go ahead. You're raising your hand.
Sorry, that was a mistake.
Okay. So, like I said, so that the next week moderator will not have to wait for us, right? So next week we are going to try to start as early as possible. 8 sharp. The lecture has started already. So thank you so much for joining today. See you next week and enjoy the rest of your evening.
Yeah. So
Thank you. Good job.
hello?
Hello?
Okay, I think the president has something for us, so please don't drop off yet.
Yeah, so
Yeah, so
please, I want you guys like
please, I want you
mention
guys
one or
like
two things that
mention
you've
one or two things that you've
learned on the social
learned
media
on the
page,
social
and
media
follow us
pages,
on
and follow
social
us
media,
on
Twitter,
social media, Twitter,
LinkedIn, and Facebook.
LinkedIn, and Facebook. So we have a WhatsApp group, and we also have
Slack,
a
Slack group
Slack
as well.
group
you can ask
also.
questions
So
there.
you can
And
ask
remember that
questions there. And remember that the goal of this meeting is to just introduce you to the most important part. And if you notice that when it started about
so
data structures and the way they are stored. It's
the
very important that you understand.
boring
You know,
part,
it sounds like the boring part, but
these
you
are
have to understand that these are
know
kind of crucial. You need
how
to
this
know
get
how this thing have been stored. You get,
here
you hear
or
new things about
let's
computer, maybe technology, ChatGPT, and some of those things.
start from the
You know,
ABC.
you need to start from the ABC before you now go to the advanced
So
level.
that's why we
So
started
that's
out.
why we started that
And
way. It
be a bit
can
boring when you're
be a
not
bit boring when you're
not
not
like
doing the crazy stuff
building
like
but
building mad application. But
ABC,
you know,
there's
if
no
you don't know ABCD, there's no way you can form letters. There's no way you can
way
pronounce some word. There's no way you can read
yes,
some
so
stuff. You get
we all
so we also recorded this meeting,
so it's going to be
so it's
good.
going to be available on our YouTube channel. So we're going to be uploading it on YouTube, and we
Sharing
are going to be sharing links to today's slide also.
you're
So
not ready
please, if you are not registered, let's say you're part of the community and you've not
page and
check our LinkedIn page. There's a link.
drop a link to
I
all
think
our
just drop a
pages.
link to our social media
So
pages.
please join, follow,
So please
ask questions.
join, follow us,
We
ask
always
questions. It's very important. We're
available to
always
any question.
available to answer any
And
question you
remember
have. And remember that
that's the main goal.
that's the main goal,
Six, then
that
you
we introduce you to the basics, then you read more, explore on your own. By the time you are coming back for next
have a
class, you
question.
already have some questions you want to ask and or some problem you want us to help you solve.
So that was all from me.
So that was all from me.
My name is
God
Anthony.
bless you. My name is Anthony
Thank
Adedayo.
you very much,
And thank you very much,
teacher.
teacher
Thank you very much,
today.
sir. Thanks for the
Adorable
briefing.
nature. God
I
bless
am
you.
shy. I am shy, please. I am shy. All right. Thank you very much,
Um,
guys.
you be shy
Um,
for me.
go ahead, please. You have a question?